So we're going to continue where we kind of left off yesterday. So on Tuesday we had a small power circuit that we had put together with a little power on LED. And then over here we started putting together something based on the Atmega 128. So remember that you have to have a crystal, whose designator is Y, with capacitors to ground, and then into the microcontroller. And this is something you can find. You can find this type of circuit in the data sheet for the microcontroller, and these values will be dependent upon the crystal you use. So the crystals we use typically have an 18 picofarad loading capacitance. Then we also had this connector for our power coming in. Remember we had these filtering caps, these bypass caps, going into a voltage regulator up top. So from here, the next thing to do on our power side is to actually power the chip. Because if you notice, the Atmega right now has a ground going to the loading crystals, but nothing actually going into the chip. So the pins we care about are these two VCC pins and the two ground pins. Now a VCC is something different. That's for the analog supply, and that's used for the analog to digital converter. Same with a ground and a ref. So we're going to leave those alone for the moment. So we're hooking up power here. What do we need to do? Are there any components we need, or do we just hook power straight in? Anybody? Go for it. Capacitors. Right. So you're going to want to have your bypass capacitors. Now you'll notice these pins look kind of strange, but 21 and 22 are a ground and a VCC, and then there's 52 and 53, which are a ground and a VCC, so they're actually pairs right next to each other. And if you have a quad package, so a square package, typically you'll have at least one set of VCC and grounds on each side if it's a very high pin count device. And that just helps to keep the currents, somewhat reasonable between all of the pins. So what type of capacitor should we be using here? Non-polarized. So we can find that by clicking on Add Part. We can go to and look just at our design cache because we've already used these. We can pick out a non-polarized or a polarized cap. So we'll just use a non-polarized for now. And we're going to need two that we're just going to drop in right around here. And we can hit Escape. We're not connected. So just a quick survey. How many of you guys have installed Allegro on your own machines? Have any of you guys had problems with it, except for Vista? So I talked with Cadence, and they do not support Vista yet. And it will maybe happen this year. It may not happen until 2008. So, sorry, unfortunately. But it should work under XP in 2000. So has anyone had problems with it? Have you guys been able to check out licenses? All right, so no problems. So I definitely would encourage the rest of you guys to install this sooner rather than later and make sure you know how to use it because this is what we're doing for the last half of the class. Yeah?
So a message popped up and said you need to have XP Pro. But I went ahead and put it on the home edition anyways, and it seems to work. Do you have any idea why it wants Pro?
I do not. So evidently OrCAD wants XP Pro, but it works anyway. It's the same with their Vista support. They plan that Vista will support Vista Professional and not any of the other packages to start with. So I don't know what feature sets they're claiming you need, but if it works. Okay, so let's go back to adding these bypass capacitors. So we have C7 and C8 now. And what we want to do is have a separate bypass capacitor for each pin. But right now, kind of this power supply is getting in the way. So remember, you can use C to center, where your mouse is, and we can select the power supply. Uh-oh. And you can watch the program crash. Did I mention you should start early with this stuff? Okay, well there's a good demo of OrCAD. Let's try it again. So I'd also recommend you save often. Yes. And if only you knew how much this software cost. Yeah. All right, so that's a good question. So while we're waiting, the question is, why do you need these bypass capacitors? So this is basically a good design practice. You can sometimes get away without using them and your system will work. But if you look at the traces on your board, you're typically going to have a pretty long trace between any given integrated circuit you have and the actual power supply rail. And so that trace is going to have it's going to take some finite amount of time for a wave of current to actually make it down. So remember in your microcontrollers that everything happens on clock edges. So if you're running at 16 megahertz, you have a 16 megahertz fundamental frequency when everything's changing. And so if you don't have these capacitors, you're basically be required to draw your current that's running the chip from that long transmission line. So it's an electromagnetics problem. But you'll notice that if you do that, you're actually going to get a brownout condition. Your voltage is going to drop significantly before the current wave can reach the device and actually power it back up. So if you put these small capacitors right next to it, and if you use non-polarized, so like a ceramic capacitor, then the devices will be drawing basically their current from that charge reservoir in the capacitor. So basically your chip will use power from the capacitor, and then after the clock edge, and as soon as you start drawing power, it's going to draw current from the power supply to recharge that capacitor. So it helps with your electromagnetic interference and your EMI immunity quite a bit by having these capacitors close by. All right, so the question is, why are you adding more right here when we already have a couple right here? So this is where there's a layer of abstraction between the schematic and the actual PC board. So remember that every component you guys see here on the schematic is going to be a physical component on the circuit board when you're done. And just because I place these things close together or far away, like if I do this versus if I do this, on the board, you have no idea where these parts are going to be relative to each other until you start your board layout. So there's going to be some significant trace length between the IC and the power source, right? And if you say, well, I'll just place the power source next to it, well, you can place it next to one power pin, but not next to all of them. So for best performance, you want to put those bypass caps right next to each chip that actually needs them. So if you guys take a look like at a PC motherboard or something like that, it's a really good example of good PC board design. And you'll see, for example, in ball grid array chips, these very large square chips in the package. If you flip over the board, a lot of times you'll see zillions of little ceramic capacitors underneath them. And they're doing the same thing. They're basically bypassing, they're bypass caps. They've helped filter your power supply coming into those devices. Does that kind of make sense? All right, so those capacitors are only needed for your power pins on any chip. The other pins don't need capacitors because that's just going to change their, their RC constant. And you want them to be fast in general. All right, so the question is, 16 megahertz is pretty low, so does EMI really matter? So it depends on what you're doing. In my research group, we do very low frequency radio research. So we're looking at frequencies between DC and about 50 kilohertz. So trying to get all of these systems as quiet as possible actually does matter for us, just from radiated noise. In the grand scheme of things, 16 megahertz is pretty slow. It's not a huge concern. So you can run these without bypass capacitors, and it'll continue to work usually. But you're still going to see that drop in your voltage rail. So this is basically just a good design practice for any system. And we're going to start with something slow so you don't notice your mistakes quite as badly. And then when you move up, you'll definitely notice these problems. Yeah?
You need a bypass capacitor on every power pin of every chip.
So the question is, do you need a bypass cap on every power pin of every chip? Good design practice says you should. Again, you can probably get away with not, but in general, you should. All right, so how do we come up with these capacitance values? So some of the devices will recommend that you have a certain capacitance coming into them. Others will not. So for example, a Max 232 line driver generally won't even mention that you should have a bypass capacitor on the power pins, and maybe or maybe it not, or maybe it doesn't matter for that particular chip. It's good design practice to put one in. These capacitors are less than a penny a piece when you start buying them in quantity, so it's not a very significant cost. So in general, you can use a 0.1 or a 1 microfarad ceramic cap as your bypass. 0.1 is probably the more common, and that's what we're actually going to be using up here. So it's just kind of a design rule of thumb. Now if you're doing something where you know it's going to be high current and switching, So for example, if we had all the ports on this microcontroller maxed out to the maximum current output capability, and you know that in your application all of them are going to be switching all the time, you'd probably want to bump up the capacitance on the input. So we're going to go back and try and add a part again and go to our design cache and grab those capacitors since they died.
Order of magnitude from like 0.1 to 1 or 1 to 10.
Yeah, so think on a kind of a log scale. So, you know, if you're changing from 1 farad to, or 1 microfarad to 2.2 microfarad, it's not a huge difference. But, you know, moving from 0.1 to 1 or 1 to 10 or 10 to 100 is a pretty good jump. So we're going to place, again, like we had done before the crash, 2 capacitors here. And we're going to go ahead and specify the values before you forget to do it. So again, you double click on it, and then you can type the value. So we're going to do 0.1 UF, so that's microfarads. We're going to do the same thing for C8. Now, remember that your nets and anything with the same net alias all gets connected together electrically. So we could leave these capacitors anywhere you want on the schematic and just have a little piece, a little net, so we can type W to start making a net. So we could just make a little piece of net coming out of each one of these. And then we can put an alias on it for 5 volts and ground. And right now this capacitor will be hooked up to your power rails. If you guys don't mind holding it down just a little bit back there. It's kind of loud. But if you hook up your nets just like this, you're not really going to remember when it comes to board layout, well, why do I have this capacitor here? Or where does it physically need to go? So technically this is perfectly okay to do, but it's not really going to help you remember why you did this. So keeping these capacitors close to the part that you actually hook them up to is a good design practice if you can. Oops. So again, you can use W to make wires, and we'll go ahead and connect together these devices. So remember, the exclamation mark comes up when Allegro or OrCAD is concerned that you're actually changing the net ownership of multiple nodes. And again, we intend for this net to connect to multiple things at the same time. So at this point, these bypass capacitors are connected. You can just clean up the look a little bit. And you know clearly where they go. Now, do you need to use a power symbol versus a net alias? Doesn't matter. Yeah?
If you have pins 21 and 52 wired together,
Yes.
and then you just need one cap for both of them, or you need one cap for 21 and one
All right.
cap?
So the question is, I have pins 21 and 52 shorted together right here, and then I have 22 and 53 shorted together here. So don't I only need one capacitor instead of 2? So remember, these pins are very far apart on the chip physically, so they're on opposite sides of the chip. And you basically want to put one of these capacitors right next to those pins. And so when we start doing board layout, I'll show you the proper ways. You basically want current to flow in from the power supply here into the capacitor, and then you want the capacitor to then flow into the pin. So the physical representation that we have right here isn't the way it's going to be laid out on the board. So right here we just say that like these 2 pins are both VCC, these are both VCC, and we're going to have 2 capacitors that are close by. So putting them close to this pin on the schematic just reminds us why we had these components here in the first place. So remember that your schematic isn't strongly correlated to the board layout as far as the physical location of components. Yeah?
So earlier you were stressing the fact that each symbol corresponds to one physical component on the board.
Correct.
In this case, could you end up repeating C7 and C8 because those pins are so far apart from one another?
Not sure I follow. So yes, I was stressing that each symbol on here basically is one component. So this is one capacitor, and this is another capacitor. So those are 2 physically separate capacitors.
So what if pins 21, 52, or 21 and 52 were on opposite sides of the chip?
They are on opposite sides of the chip.
That's why you put.
That's why there are 2 capacitors.
Oh, okay.
How do you designate where they're supposed to be?
All right, so the question is, how do you designate where they're supposed to be? You can either write a little text note to yourself to try and help you remember. Some other competing schematic capture programs will actually let you place notes that will show up during your layout, which is a nice feature. Otherwise, you don't. So for us right here, for example, we have these two capacitors, and you can lay out your board where C7 is next to 21 or C7 is next to 52. And you won't know unless you annotate it here. Not that it really matters, but no easy way, unfortunately. Yeah?
So are the two VCCs and ground just so if they're on opposite sides of the chip, just so there are two entryways?
Yeah, so there are multiple power rails and ground rails in the chip to kind of load balance across the die itself. So that way you don't have a huge voltage drop across the die as you're distributing power inside the chip. Now, back on this whole point of why are we connecting them this way on the schematic, and are these pins shorted together directly, or what's going on? Remember that every net with the same net alias is connected together. So if we step back just a little bit here, that means that pins 21 and 52 of that mega, and pin 1 of our voltage regulator, and C6, C4, C7, and C8 all are connected together. And that's what you want, right? You want your power supply to be powering these two capacitors for the charge reservoir. You want it to be powering these two bypass caps, which in turn power these two power pins. So remember that everything that's net aliased together is electrically connected together. The physical representation on the circuit board is going to be different than what you see in the schematic. The schematic just indicates what eventually needs to be connected together. So is that pretty clear? So that's an important point. Yeah?
Yeah, just a side question. I was wondering, how do you control whether the wires that you draw across the components will get touched?
Okay.
Like exclamation mark, right? When do we know that they shouldn't touch?
All right, so the question is, when do you worry about the exclamation mark and when do you not?
So by default, the program will guess whether it should connect.
Well, let's run through a quick example. So if you have, for example, the analog reference voltage, if I just run across this other trace, there's no exclamation mark, because it knows that you're just crossing another trace and that nothing's going to change ownership. Now, if you run it to a node, things start happening. And if we run it across these two nodes, you're shorting out this capacitor. So if I was to click right here, you're going to short VCC and ground together,
Oh, okay. So
right? Because that's this upper node right here and this lower node here. So this is VCC or 5V0, and this is ground.
So the program decides itself when it hits a node, then it tries to connect it.
Right, so the program itself will generate the exclamation when it determines that you're going to be connecting to multiple different nets. So for example, if I just pull this out and I just put it right here to our input voltage, right, and click, it's going to connect the two of them together. And you can see because there's still that junction, right? And I can make that more clear by moving this over a little bit. So you can still see the junction, right? But there's no warning box because you're only connecting to one new net. You're not shorting nets together.
And also, does the software simulate the circuit as well?
All right, so then the other question is, does the software simulate this circuit? So this software does not. This is just schematic capture. So there's PSpice where you can simulate your analog circuits, and there are some packages that will simulate some digital systems. But the thing to remember is that right here I have this large microcontroller. And how do you simulate what this microcontroller is? This microcontroller is a computer. It's something you program. And as you guys have seen in the first half of the class, it can do just about anything you want on all of these I/O lines. So how do you properly simulate that? Well, some of the more advanced packages will have things where you can define what the pin states are at given times or at given changes. But in general, you don't simulate these systems, unfortunately. So any other questions? Okay, so at this point we have a powered up chip, and a VCC, a ground, and a ref should be connected. So this is not going to be a fully completed schematic. It's just going to be something to give you guys a good start. So let's say that we want to now connect a bunch of LEDs together. We're going to have 8 separate LEDs connected to port A. And just to make this example a little bit harder, we're going to put those LEDs on another page of the schematic. And we're going to use buses. So this is the place bus icon. So if you click on it, you can begin drawing a bus. You'll notice this bus is quite a bit thicker than the nets you've been drawing before. So you can see the difference between a net down here and a bus up here. So the bus is the thicker blue. Remember that a bus is a series of multiple connections together. So we're going to alias this bus, and we're going to call it PA 0.7. And remember that having the square brackets and then 0, dot, dot, and another number, or any two numbers with two periods in between, is how you specify a sequence of traces or nets. So we're going to click OK with that and alias this whole bus. So now this bus contains nets PA0, PA1, PA2, and so forth up to PA7. That's just an arbitrary name. That doesn't have to correspond to here. We could call it LED 0.7, or whatever name is useful for you to remember. Yeah?
Does this notation actually need something to the program, or is that just...
Yes, so this notation is important for capture itself. It's not just the way that it's done in the industry. If you don't label your buses like this, it gets complicated as to what nets are actually contained inside that bus. So now the problem is that we want to go from a bus to a net to actually connect each of these pins. And you can't just draw a wire straight into the bus. It's a bad idea. So we're going to use the bus entry. So that's this kind of / looking icon. So you can click on it and you can see we now have a slash. And remember that if you hit R, you can rotate apart. So we're going to allow these slashes to go down. This is just for aesthetics. And we're going to place 8 of these together. So we now have these bus entry points. So from these lines, we can actually draw a net. So again, to begin drawing nets, you can either click on this button or type W, and you just connect your pins to these bus entry points. Now you'll notice here that it pops up a warning if you go too far. That's because you're about to short 2 bus entry points together. So when you see the little exclamation mark, do pay attention to it. So we're just going to quickly wire these together. And once you have these nets created, you have to name them. Otherwise it's not clear which net is which net on the bus. So you name these nets the same way you name any other net with a net alias. So we're going to call the first one PA0. Now if you end the net name in a number, it will auto increment for you. So if we start with PA0, we can click on this first net, and it says PA0. If we now click on the net below it, it auto increments to 1. So this makes your life a lot easier when you're placing multiple net aliases of a sequence. So at this point, we now have a bus with 8 bits of port A. Yeah?
So you attach an alias to a bus or a net by just putting the bottom or top of the
yes. All right.
the text box onto the...
So as far as how do you actually place these aliases? So when you click OK, you basically click your cursor itself on the device, on the entity that you want to have that alias. And so it depends on where your cursor is and which way your alias is rotated, because you can see right now it's below and now it's above, but it stays centered around your cursor. So just click with your cursor on the net to alias it. Yeah.
And actually, can you just drag bus wire close to the pins and play it with touch and stretch it back so that you don't have to draw it?
So the question is, can you just drag this bus onto the pins and then drag it back to have all these nets come out? And you can't, unfortunately, because the bus and the nets are different entity types.
Okay, so
And you also have to be careful when you start dragging components around. So I guess we can do this right now. So if I start dragging here, you can change net connectivities. So you can see in the upper left-hand corner we're starting to short things together, and also down the lower left corner of the screen. And you get the exclamation mark because of that. So dragging gets dangerous. Be careful. Make sure you select your traces if you can when you're dragging components.
And so you're including the controller button to copy those aliases around?
No, so when I was placing these multiple aliases, you create the first alias by clicking on the alias icon, and you type PA0. right?
Yeah.
And then you hit OK. And then all you, sorry, my mouse is acting up. Hello?
Escape.
There we go. So if you click on one entity, right, it'll put PA0. Then you can click on the next one, and it'll put PA1. Then you can click on the next one, it'll put PA2, and it'll just keep auto-incrementing as you click. You don't have to hold any special keys.
What
Yeah.
happens if the aliases of the nets you have going into the bus aren't consistent with what you named the bus? You go up to like 9 or something and you only have 0 seconds.
So the question is, what if your net aliases are inconsistent with the bus naming? I'm not sure. I'd recommend you not try. This mouse is obnoxious. Excuse me just a second. Let's get a real mouse. That also doesn't work. Lovely. Well, that doesn't work.
If you got batteries, I got a wireless mouse.
Yeah, but it's not even recognizing my wired mouse.
Yeah, but that's what
All right, here we go. It's behaving a little better. So you can clean up your nets by just clicking on parts to delete, just to make things look nice. All right, so let's go add another page to the schematic, because we're eventually going to put our LEDs in a separate page just to make life miserable and show you how to do it. So if we minimize that, remember that we have this actual project view, and you can click on your design resources and then on the name of your project and on the schematic. And right now we have that one page that we renamed to Microcontroller, UC. So at this point we can right click up here on schematic and then click on new page, and that will add a new schematic page to our design and ask you for the name you want. So we'll call it LEDs. So notice you now have a second page pop up. So we can go double click and open up that second page of the schematic, and it reverts us back to a letter size sheet of paper. You can go on window to actually maneuver around between the different schematic pages, which may be useful. So we're going to want a couple different things on our new page. Namely, we're going to need the bus itself because we're actually connecting this all together, but we're also probably going to need either VCC or ground since we're driving these LEDs. So since you guys have seen these atmels before, which one of the two do we need? Do we need VCC or do we need ground to connect the LEDs to a pin? Which one is a better design choice given our processor? VCC, that's correct. Remember that your chip can sink more current than it can source. So to do that, we're going to place another wire, and we'll just place it nearby. It's just an empty piece of net. And we'll alias that net to 5V0, which is our VCC. So we now have a little piece of floating power. Now since we're going off page, we're going to use the off page connector. So that's this icon right here. You can click on it, and there's two choices you have. You can go to the left or to the right. And we want to have our text on the right hand side, so we're going to use the left icon. And now we'll place our off-page connectors. You'll notice right here that you have a square box on this one connector, and that indicates that the nets are not actually connected together. So that can be very dangerous when you're making a schematic where you have an off-page connector and the net, and the two of them don't follow each other. So the way to avoid this is you can grab on the symbol for the actual off-page connector, move it around, and make sure it stays connected with the net or bus. So the 5V0 is working okay. The actual bus connector is not. So we're going to drag the bus over. Maybe we have to rename it first. And now they're connected. So again, to bring up this menu where you rename text or designators, you just double click on the text. And so we're going to rename our 5 volt VCC rail off-page connector to 5V0 to be consistent. So at this point, both of these connectors are connected. Now we're going to need these exact same connectors on the other page of the schematic. So you can redraw it, which you guys have already seen how to do, or you can copy and paste. And since we're just using the same thing, we'll select a little piece of both. Then we can go to Edit and Copy, or you can use Control-C, switch pages, and then we can paste it. Now when you paste it, you'll notice it doesn't just drop it, it turns your cursor into a view of everything you copied. So if you copy an entire page worth of schematics, your cursor is going to have an entire page of stuff following it. So make sure you have enough space in your destination to actually place these parts. So we're going to place them here in the upper left, shrink things down a little bit. And we now have our bus and our power rail on this new page.
Since they're all the same, you only need one 5 VCC off-page connector for on each page, right?
Correct. So you only need one off-page connector for each net or bus per page. So even if you have 30 different places where you need VCC, you only need one VCC off-page connector. Because as soon as you bring this in, this says, hey, I'm going off page to 5V0, and it says on this page, I now have a net named 5V0, and those will all be connected together. Yeah?
Is there a way to tell if you have multiple pages which connector goes to which page?
So the question is, if you have multiple pages, is there a way to tell which nets are on which pages? And you can, I can't remember off the top of my head how to do it, but there's a way you can back annotate or annotate, and it will show you what pages after the off-page connector have that symbol. I'll look into it. Yeah.
If you wanted to, you use the off-page right connector so the text is on the left side here.
All right, so the question is, can we use the off-page right connector? Absolutely, so we'll do that. So at this point, we just have the nets, but they're not properly connected to the other pages on the schematic. So we'll go back to place an off-page connector, and we're going to use the right off-page connector. And we're going to relabel these by double-clicking and then typing the net name or the bus name. And there you go. So any questions about these buses or the off-page connectors? Okay, so at this point, let's add a couple LEDs. So we're going to add a part. And which library is going to have LEDs in it, most likely? Discrete. It's a discrete component. So we'll go to discrete. And remember, you can search through the library by scrolling or by typing in the part name. And we're going to expect the LED part name to be something like LED. Now, if you remember, we already have one of these in our design cache, so it's even easier just to hit design cache and select LED. So our LEDs are going to be active high or low? Low. So you want the LEDs to be basically pointing towards the port. So if we put them in this direction, that'll probably be the proper direction. Sorry, backwards. Now you notice that the arrows are kind of upside down now, which may disturb you. You can also right-click and mirror if it makes you feel any better. It doesn't really matter. Okay, what else do we need aside from an LED? Resistor. And what type of resistor is it? It's a current limiting resistor. So is it series or parallel? Series, all right. So let's make this a red LED. And again, the resistance value you use will be based upon the drop across this LED, which is going to be in the data sheet for the particular LED you use. And it's going to be based upon the total voltage between these 2 points. So if this is a 5-volt rail, and we have a 2-volt drop right here, so you have 3 volts that you have to burn off in the resistor. You have to look at the current flowing through the LED, which is specified in the data sheet, so that's usually like 20 milliamps. So you can figure out the proper resistance value. So we'll just use about 180, which is pretty common. And at this point, we can start wiring them together. And all you have to do is wire from VCC into the LED, and the LED into the bus. Now we're going to be making a lot of these, so again you can copy and paste by selecting and then going to edit and copy, or we'll just hit Control C and then Control V. And you can paste again without having to recopy and make multiples of these in a row. So how do we connect into the bus? Walk me through it. Oh, question.
Can you connect that resistor to LED directly without using a wire?
So the question is, can you connect the LED and the resistor directly without using a net? No, it won't let me click. So you need a piece of net. Good question, though. All right, so walk me through adding this to the bus. What do we need first? Before you have a bus entry, what do you need? A bus. So let's draw the rest of the bus we need. All right, we have a bus. Now what do we need? A net. Well, where's you going to draw your net to? You need a bus entry. And you can make it go up or down. We'll just make it go down. So you can hit R to rotate. Now what do you need, Bernie?
Nets.
Nets. All right. So we're going to connect these together. All right, so is that it? You need your net aliases. So let's start with PA4. And let's just have this be the upper 4 bits of that port. Anything else? No, you're done. So we now have this second page which just has the LEDs going into the bus. And we have our power and our bus connected through off-page connectors to the first page. We can switch back to the first page, where those connectors come in and actually connect to the microcontroller and to your power supply circuitry. So any questions on that part? We good? All right, so at this point, let's say that we're not going to use any of the connections on port C. So what do you need to do to indicate that you know you're not using a connection on this IC? No connects. So this is the place no connect. It's very easy to use. It brings up a big X, and you just click on any one of these square boxes, and it puts a small X indicating that it's not connected. So at this point, it's clear from the schematic that you're not connecting port C to anything. Now, yeah, question. So the question is, how do you reactivate that if you made a mistake? So you can double click on a pin, and it'll bring up the pin properties page. So this is like what we did before with nets to see what a net was named. And here you can see there's a check mark that says is no connect. So you can uncheck that and close it, and that pin has reverted back to a regular connection. Comment is it looks tedious. Well, it is. So this definitely takes a lot of patience to get everything done correctly the first time. Because remember, everything that you do in the schematic, this is just the first half of the process, or really the first third. The schematic indicates how all these parts are put together, and it's a representation of the physical parts that will be on your board. Your PC board layout is how you actually physically connect these things together and physically place them on a board. And then the last third is smoke testing it, plugging it in and making sure it doesn't start smoking. So this is just the beginning, but the more time and the better you perform at this very first stage, the less cost you're going to run into later on. Each time you fab a board, it's going to cost a couple $100 most likely, unless you're doing small one-offs like this where it may be a $33 board. So spending another hour looking over your schematic will save you hundreds of dollars later on in board layout. And once you start stuffing boards, you may have single PC boards that are thousands of dollars to assemble. So it adds up fast. So take your time on the schematic. Okay, so any questions on what we've covered so far? The basic parts, the basic support you need on a microcontroller, where these libraries are, how to connect nets to buses, new schematic pages, off-page connectors. Yeah?
So given that none of this seems very complicated, what do you get in this really expensive program over like the freeware layout?
So the question is that none of this seems very complicated, so what are you getting over a freeware layout program? I'll just leave that as an exercise to you. So the layout engine that we use on this program is quite powerful. There's some library management utilities, so if you have a lot of people working on a lot of schematics with a lot of different parts, it can maintain it much better than the freeware things. And you get commercial support and software that still crashes. So, yeah, unfortunately. Yeah?
This is more of a question of repeated features that could be used as now. When we're doing the actual PCB layout, we're doing routing.
Correct. So when you're doing the PC board layout, you will be routing it by hand. Yes.
Rather than auto.
Yes, you will not be auto-routing in this class.
Why is that?
So why is the question? Well, first off, I'm assuming that no one in here's done PC board layout before. There's probably a few of you guys who have. So to start with, we got one. So to start doing PC board layout, it's best to do it by hand where you actually know what's involved in getting everything to work together. There are auto routers out there, however, they're not very good. And on most of the board designs I'd done up until about last year, I had never had an auto router that was able to auto route them to 100% completion when you can do it by hand to 100%. Now I found a Cadence tool called Spectra, which will auto route very fast and very nice for you if you don't care about signal integrity. The other problem you have is that as you move into what's called a mixed signal system, so if you have analog and digital together, which a lot of systems will have, then you really have to be careful how you do your layouts so you're not coupling noise into your analog side from your digital side. So a lot of those types of systems you will end up routing by hand regardless, just because that's the only way you can ensure your signal integrity and densities. In the commercial world, a lot of high-end manufacturers do everything by hand routing. They have people who that's their whole job is to hand route because they claim you can get higher densities than the auto router. It may take you a little longer, but and the other thing is that if you're starting out, it's best to know what the tools are doing inside before you just let a tool do it for you. So any other questions? Yeah.
So from this schematic, do we have something that generates some sort of layout with routed in advance that we can fix it up later?
All right, so the question is, from the schematic, is there something that kind of generates the beginnings of your layout? And there is, and we'll cover that next week. So there's a way that you can create what's called a net list, which basically tells you every node of every component and what nets they're connected to. And from that, the layout software will automatically import it and begin the layout process. So that's all of next week. But it is automatic. You're not doing this all for naught. So any other questions? Okay, so what do you do if you need to use a part that's not in Capture? So we have all these libraries that have a lot of parts, but there are a lot of parts that don't exist in here. So that's when you have to actually create your own part library. So if you go to the File menu and you say New, and we're going to say New Library. So we're going to assume that you guys haven't already created parts libraries. If you have, you can just open that library and begin editing parts inside of it. But to start with, we're going to create a new library. It'll ask you where you want to add it to a project. You can either make a new project that just has that library in it, or we can put it in our current project. So we started this last time. It's called Lecture 15, even though this is 16. But we'll go ahead and put it into our current project. And you click OK. And now it appears that absolutely nothing has happened. But if you go back to your project viewer, so that's this little tab on the side, we now have the folder library, and under library it says library 1. Well, we also can save this library as a different name, and we'll put it where our project is currently saved. And we'll call this EE292. You notice it now has changed the name. If we click the plus, you'll see that there's a library cache, but there's nothing in the library itself. So at this point, you've created a new library. If you already have a library, you can just right-click on the word library and say Add File and import your existing library to add parts to. So once you have your library listed, you can click on it and then right-click and create a new part. So this is how we're going to begin creating a new schematic symbol to use for a part that is currently not supported inside of OrCAD or Allegro. So this is the new part properties dialog. So your part needs a name. And so for our new part, I've selected an Atmel microcontroller that's not in there. It's an ATtiny24. It's a very small chip. That way it'll be fast for us to do here in class. Here's kind of the footprint layouts for two different packages. So we'll call it ATtiny24. And you'll notice that there are two different packages here, and the pin numbers don't match between the two packages. So if you create a part and that same part has multiple packages that have different layouts, that have different pin layouts, pin configurations, you need to create separate parts in your library. If you don't, you're going to scramble what gets connected together later on when we begin the layout process. So we're going to specify that we're making this as the SOIC. So we're going to go back here and we're going to say ATtiny24_SOIC. And SOIC is a surface mount, relatively large package. It asks for the part reference prefix. It's what was on the little pop quiz earlier. So this is an integrated circuit, so it's U. You also can put in a PCB footprint if you already know what it is, or if you have footprints already. We'll be adding the footprints later on. If you have, for example, a package that has 4 different op amps in one package, you can say that there are 4 parts per package. This is a single microcontroller. Everything you do in this class will have a single device inside the package, so we'll leave it as one. And you probably want your pin numbers to be visible, so that way you can check against the data sheet later on and make sure you did everything okay. So we'll hit OK at this point, and it brings up this new window where we can start drawing a use something with some value. So if we look at our data sheet, there are a lot of different pins that we're going to need to use. And we'll try and just roll this around a little so we can see what's going on. So to start with, there's this blue dotted outline, and that's the outline of the schematic symbol itself. So when you place pins, so this is a pin, it's got the number 1 next to a little line icon. If you click on that, we can create a new pin, and we'll name this pin VCC. It's going to be pin number 1, and there are a couple other options. You can have different shapes, so if you have a clock, or if you have a dot, which means it's an inverted input, or an inverted clock input, or regular lines or short lines or a non-existent line. So we'll stick with everything with regular lines for now unless you have a special case. There's also type. So here you can have 3-state, so I think you all are familiar with what 3-state is at this point. And then you can specify a line as being either bidirectional input, output, or open collector, open emitter. You also have passive and power. Now this will help when you're running some of the design rule checks, where it'll make sure that you've connected an input to an output and vice versa. It'll make sure that powers are connected to each other and not connected to inputs or outputs. Now, we have found in our research group that a lot of this stuff gets in the way, and it gives you a lot of false errors because you're connecting pins that are inputs to voltage rails because you want to set them a specific way, and that'll generate an error condition. So we leave everything as passive on all of our components. If you leave it as passive, you're not going to have any complaints from the design rule check saying that you haven't connected things properly, because half the time it doesn't know what it's talking about anyway. If you specify your power pins as being power, they often will not show up on the schematic. So if you have more than one voltage rail, it gets very complicated to try and figure out what power rail is connected to what IC. So again, we're going to leave everything set as passive for all of our pins, even though this is a power pin. So if we click OK, you now can drag around, and we're not clicking, we're just moving the mouse, and you can see that the pin will follow and place anywhere on this little outline. So we're going to place it over here on the right-hand side. And remember that you can use I, O, and C to maneuver around, even while you're dragging something. So we'll click and we'll put VCC there. So you'll notice now that you have a pin, the pin label is VCC, that's its function. On the outside you have a number 1, that's the pin number, and that's the pin number on our package right over here. So that's the very first thing that we've put down. You'll notice we don't have enough space here to put all of our pins. So if you click on a corner, you can drag and make this much larger. Now you may notice that I'm putting VCC somewhere else. I'm not putting it in the upper left. Remember that the schematic symbols are just a representation of something physical on the outside. The number here is what determines where this net physically goes to a chip once you start layout. It has no impact on how the chip actually looks in the schematic capture software. So we're going to put our power and grounds on this lower right, kind of like we did before with the Atmega 128. So let's go ahead and add our ground pin. So again, we'll use the pin tool. The signal name is GND, it's a line, and it's pin number 14 for this package. So we now have 2 pins together. At this point, you can continue adding all of these pins. There's a lot of them here. If you guys look at the Atmega 2560, there are 100 of them. It takes a long time, and if you mess up one pin number, your whole board gets messed up when you get it back from fab a week later. So take your time on all this stuff, and this is when I would highly recommend that when you have a partner, since you guys all have partners, if one of you all does the actual package design here, have the other one read over and check everything, or read through it together in pairs. If you mess up one pin, you mess up your whole board. That's life.
Does that
Yeah.
not have libraries that you can download?
So the question is, does Atmel not have libraries where you can just import these? And to my knowledge, Atmel does not. Some companies do. For example, Analog Devices has I think just about every chip they have in a library that you can download. Most vendors don't. You're stuck. Also, different CAD tool programs and CAD tool vendors will have different libraries included. So check through the libraries, you can hunt around a little bit, and then at some point you're just going to have to give up and start making your own devices. So let's just add another pin or two. So we can place another pin, and we'll call this PB0, and I'm going to ignore the actual special functions of this pin. When you all are making actual schematic component labels, you need to have all of this information in there. It's going to make your life a lot easier when you're hooking this up. But for time in this class, we're just going to skip through it and just put the actual pin name. So we have PB0. Now you notice that PB1 is pin 3, that's the next one. And just like the net aliases, the pins auto-increment, so you can just click. If we click again, we're going to get PB2, but you notice that PB2 is a different pin number. So you'll have to double-click and change the pin number to 5 and hit OK. So for the sake of time, since we only have about 5 more minutes left, let's assume that this is your entire chip. At this point, you can shrink your package down, because the less space that you take up in your schematic, the better. Oops. So if you scroll off into Never Never Land like just happened, it helps to zoom out, because you never know which direction it was actually scrolling, and then put your mouse where you want to go and zoom back in. So this part's making a big mess of my pins. So I think you guys will have a lot of fun with this software. So you can see that there's nothing technically complex with doing this. It just can get very tedious. I'm not even sure I want to try dragging this. It's not going to let me. Fine. So at this point, if we save this part as is, this blue dotted outline wouldn't be visible. And if we go back to our schematic and actually look at parts that we have, you'll notice there's a nice border. And the border is useful for a lot of components, especially ICs. Now for some of these things like capacitors or your resistors, you obviously don't want a border. So you can draw these special symbols by using these line tools. So you can draw any shapes you want. And in our case, since we're having an IC, we'll use the square tool. We're just going to draw a bounding box around this symbol. And it helps to clean up your text in your library, because this way, every time you place this part, the text will appear in the same position. And if you don't clean up your text now, every time you add this part to a design, you're going to have to clean it up then. Yeah, question?
What do you do for value?
All right, so what do you do for value? So you leave value alone, typically. And this will auto-fill in with the part name from the library. So for a resistor, for example, if your resistor is named resistor, this will fill in with resistor when you place it. Now, if you're making a special component, right, where you're having one value of resistor be the whole component, then you'd name the part with that value in there, and that would become the name of value. So at this point, you can close, we'll go back to full screen here. You can go ahead and close this window, and it'll ask if you want to save changes to this part. So I'd recommend you save changes to the part. So now back on our schematic, if we want to actually insert this part, we can go to Add New Part. And then we have to add the library. Well, the library is already added since we added it to this project before. You notice we have one part in our library now. We can click OK, and the part now shows up on our schematic. Yeah?
Why did you add the solid? What was basically the dotted line box?
Okay, so what was the difference between the dotted line and the solid line when you're adding the parts? So the dotted line basically shows where you're putting your pins around. And the solid line is a line that you can actually see once you've created it. Yeah?
Is there a function where it automatically spaces
All right, so the question is there a function to automatically space the pins to an equal distance? So there's a grid spacing inside of this. And right now we have the grid spacing on, which is why these are all spaced evenly. And it will fix the pins to regular grid spacings. You can change the grid. I think it's under like global spacing or something like that. Grid display. Something like that. So any other questions? Okay, so at this point, you guys should have everything you need to actually begin drawing schematics to create your own custom components and make schematics based on those parts. So beginning next week, we'll actually move from here into layout. So on Tuesday, we'll show the transition from a completed schematic, which I'll finish up this weekend, to an actual PC board and how to begin routing. If you haven't already, please install the software over the weekend and start using it. It's got a non-zero learning curve, as easy as it may look up here. So please get started, and have a great weekend.